G'day, in this video we're going to be unpacking how particle accelerators work. This covers dot point 8.5.3. We're looking at the operation and role of particle accelerators and how that helped in obtaining evidence that tests and or validates aspects of theories, including the standard model of matter. Effectively, as we talked about in the previous video, to understand the standard model of matter and discover particles, whether composite or fundamental, accelerating particles to higher speeds and causing them to collide with other particles and observing their interactions is foundational to the experimental framework used in this field. As such, to conduct these experiments, we need apparatus which is able to get particles to accelerate at high velocity. So first off, we're going to talk about the need for particle accelerators and then introduce some basics principles which explain the design of accelerators such as cyclotrons and synchrotrons. So there are many types of particle accelerators, but their main concept is all the same. Get a particle that's charged, make it go fast, smash it into something else. That's the general concept. Some accelerators are, relatively speaking, small scale. A lot of the time these are cyclotrons. Last lesson we already looked at the idea that we could have a particle accelerate linearly. The most famous particle accelerator would be the one which is at CERN, the LHC, or the Large Hadron Collider. The largest synchrotron in this whole system is 27 kilometers in circumference. So we're first going to have a little bit of a look at the operation of a cyclotron. So cyclotrons have two semicircular sections to them, which are commonly referred to as Ds because a semicircle is in the shape of a D. And these essentially act as charge zones. And these zones can oscillate in their charge. This is achieved by having a square wave of electric current. Effectively, it's AC. A charge is placed inside this area and is able to be accelerated by being attracted to one side of the Ds and repelled by the other side of the Ds. If we were to ignore the red dotted lines here for the moment, and let's just say I placed a proton right in the middle of the two Ds, and I was flipping the polarity of the two Ds. Essentially, this would push and pull the proton in opposing directions. The proton would accelerate towards one D and inside it, and when we flip the polarity, it would then slow down, stop, and return, accelerating in the opposite direction. Essentially, all you're going to be doing is making the proton oscillate backwards and forwards with very little change. In order for this attraction and repulsion from the Ds to cause continuous gains in speed, rather than slowing the object down and re-accelerating it to a high speed again, we can make the particle move in a circular path. And as it gets faster and faster and faster, the path it takes gets larger and larger and larger until it spirals out to the edge of the circle. The way that we make the charged particle move in a circle is by applying a magnetic field through the Ds. By right-hand rule, as the charged particle moves perpendicularly to the field, it's going to experience a force which is perpendicular to both vectors. This perpendicular force effectively acts as a centripetal force, making the particle turn back in the opposite direction. This is effectively maintain the speed of the particle as it moves through one of the Ds and makes it exit the D, keeping its velocity. At this stage, the Ds flip polarity, and the particle is repelled from the D it just exited and attracted towards the D which it is now moving towards. This increases the velocity of the particle, and again, as it moves through the magnetic field, it will start to move in a circular path back towards the opposing D. And again, the charge of the two Ds flip. The particle moves through the D but starts to accelerate by changing direction and essentially does a 180-degree turn, moves into the other D, the charges flip, it speeds up again, turns around, speeds up through the next transition, turns around, speeds up through the next transition, and so on. And again, as it spirals and accelerates through the gap between the two Ds, increasing speed each time, it's going to end up having quite a high velocity as it exits through the release point. However, this is not the only way that we can accelerate particles. Synchrotrons and linear accelerators use similar principles to accelerate their particles. In these setups, we have series of plates, and these plates can have potentials applied to them which generate electric fields. Similarly to the cyclotron, these fields oscillate in polarity in such a way where the plate that is in front of the particle is attracting and the plate which is behind the particle is repelling. So to demonstrate, I'm going to show what happens to the electron as it moves through our accelerator. In step 1, it's going to be in between the first and second plate. In step 2, it's going to be in between the second and third. Step 3 is going to be between the third and fourth, and step 4 is going to be between the fourth and fifth. So essentially, we're watching this electron progress through the accelerator at different periods of time. At the first point in time, the odd plates are going to be negative in charge, and the even plates are going to be positive in charge. However, in step 2, this polarity flips. The odd plates will be positive, and the even plates will be negative. At the third point in time, the setup will look like the first. And for the fourth time period, the plates will flip again and look like the second. In each instance, there is a negative plate behind the electron and a positive plate in front of the electron. At each point in time, the attracting and repelling forces are accelerating the particle to the right, meaning that not only is it going to move to the right, but it will continue to pick up speed as it does so. In particle accelerators, we don't just use fields to increase the speed of the particle, but we may also need to use fields to cause accelerations that lead to changes in direction. Similar to other apparatus that you've seen before, if we are increasing speed by using an electric field, we're going to change direction using a magnetic field. And this change in direction will obey our classic right-hand rule. It's also important to note that we use magnetic fields in these accelerators to keep the beam focused and to keep the particle moving in the exact direction that we want it to. Let's draw a little bit of a diagram to show how magnetic fields can be used to accelerate particles around, say, a curve or a bend, which is particularly important for a synchrotron, but for our linear accelerator also features as a necessary requirement, as the beam, even though it may get accelerated linearly, may still diverge and have to bend. And if we remember the detector as well, the beam had to move upwards. So we need to use magnetic fields to achieve all of that. So in this scenario, we have a positively charged particle moving along a track. Its velocity is currently up, but there needs to be a force, the centripetal force, or the force caused by the magnetic field, which at this stage points directly to the left. This will cause the particle to move in an anti-clockwise direction. According to the right-hand rule, for this to be achieved, the magnetic field needs to point into the page at all points to cause accelerations which point inward and make the particle move in an anti-clockwise direction. This holds true even at the end of the track where the right-hand rule is still maintained. There are some key similarities and differences between synchrotrons and linear accelerators, and I just wanted to take a little bit of time to compare them now. For a linear accelerator, the particles travel in a straight line, whereas for a synchrotron, they travel in a circular or polygonal loop. It may not be a perfect circle, but there'll be some sort of cyclic nature to it. For the linear accelerator, because the particle doesn't return to the accelerator at the beginning, it only gets that acceleration once. Whatever's been set up to accelerate the particle at the beginning of its travel, that's it. Whereas for a synchrotron, because it moves in a loop, the particle continues to pass the accelerating plate, which means you can increase the speed of the particle multiple times. In a linear accelerator, mostly we're doing beam focusing. Maybe we have to change the path of the particle slightly to, say, hit a detector. But for a synchrotron, if you're going to get the particle to move in a circle, or at least a circuit path, you're going to need to be able to not only focus the beam, but bend the beam. For both accelerators, as the particle accelerates through the plates, you're going to have to synchronize the rate at which the electric plates shift from being positive to negative. As the particle gets faster, the frequency of that oscillation is going to have to increase. For a linear accelerator, you can kind of do the math and predict the rate at which the particle is going to accelerate and set that sort of in a predetermined way. However, for a synchrotron, it's a little bit more complex because as you're moving the particle around the circuit, you're able to monitor and measure its speed. And as such, you can use a computer to essentially match that frequency as well as a magnetic field strength to keep it moving on its path and continue to accelerate it as it moves through the accelerators as it completes all of its laps. Thank you very much. In the next video, we're going to start looking at how the standard model of matter permeates many parts of the course, revisit some of those elements, and talk about where the standard model of matter fits. But until then, have a good one.